interesting intersections to discuss with you guys today. We'll cover environmental and in-field sensors, health and movement tracking technology, computational improvements, which is where the majority of my research applies, and imaging technology. So firstly, onto environmental sensors. Audio sensors are an upcoming technology in the livestock industry for the detection and analysis of disease. These are implemented in pig barns to record noises such as coughing that indicate respiratory distress. The collected audio is transformed into a spectrogram that reflects the sound changes across time and frequency, and these are applied to a trained machine learning model. The machine learning model is able to classify sounds as being concerning or indicative of disease or not. And they can be used to even differentiate between sounds of respiratory distress caused by different diseases, such as swine influenza, and environmental factors like dust or high ammonia. Research found that using these types of audio sensors in swine barns actually allowed for disease detection 3 to 5 days earlier than it might have been detected by personnel. Particulate and pollutant sensors are also very important technologies in environmental epidemiology when calculating the amount of exposure populations experience. In particular, portable and wearable sensors are becoming more and more attractive due to their low cost and mobility. Here we can see on the left, we can see a wearable gas sensor, and on the right, you can see a portable particulate sensor. While recent studies into the use of particulate and pollutant sensors have shown promising results, especially in detecting nitric oxide, carbon monoxide, nitrogen dioxide, and particles less than 2.5 nanometers, there have been reports that these sensors are very sensitive to changes in temperature, humidity, wind velocity, and the specific particulates themselves. So it would be really interesting to see how electrical engineering could be applied to combat these issues. Environmental sensors have also been deployed into wastewater or sewage, and these have been very beneficial for epidemiology. In particular, we have seen the use of biosensors that are capable of detecting small amounts of compounds and chemicals or pathogen DNA. Today, I'm only going to touch on the most relevant biosensors, which are based on electrochemistry. These involve often gold electrodes with aptamers attached. Aptamers are a short single-stranded DNA molecule that's specific for certain molecules or their target molecule. Examples include arsenic and cocaine. And when the target molecule binds the aptamer, it causes an electron transfer that can be detected by electrochemical impedance spectroscopy. And this indicates detection of the molecule. Because of the use of nanostructured electrodes, this technology is actually ultra-sensitive and has pretty good long-term stability. So it's pretty good for, if it would be possible to scale this up. And because of how specific aptamers are, the applications of this are pretty endless. You could find an aptamer for a lot of different compounds and molecules. So moving on to health and movement trackers. With the promise of smartphones across the world, the use of GPS and Bluetooth data has become invaluable in modeling and analyzing potential transmission events. The detection of contacts was quite successfully used during COVID in several countries through the use of the Google Apple exposure notification apps, which use Bluetooth to detect phones that are within 6 foot or 2 meters of each other for at least 15 minutes. If one of the individuals tested positive in the near future, all phones that had been indicated as a contact that had the app enabled would be notified of their exposure risk. In the UK, it was estimated that for every percentage point increase in user uptake, COVID infections were reduced by 2.3%. And in Washington state, in the first 4 months of implementation, it was estimated that 5,500 COVID infections were avoided. Mobility data like that was provided by SafeGraph, which details the movement of people and their presence at points of interest, such as stores, businesses, schools, hospitals. This can be used to create accurate contact networks of individuals that can be incorporated into epidemiological models that simulate the transmission of disease and make these models more accurate. Tracking animals can also be very beneficial in veterinary epidemiology research and disease control. It's become common practice to use RFID-based ear tags to manage detailed information about individual animals. In the swine industry, this is being used to track characteristics of the animal, such as their weight, and also to monitor their behavior for signs of disease. In cases of both chronic and infectious disease, animals can become lethargic, fatigued, and anorexic due to the increased stress of illness. And this is going to impact their ability to move around and to eat and drink water. So by attaching antenna to the water feeders and feed troughs, we can actually measure the frequency of the pig's visits to these areas. And abnormalities can be identified through this, and this allows for disease to either be identified or controlled earlier, or treated depending on the disease. Studies using RFID tags for such disease monitoring have reported pretty good high sensitivity and specificity for identifying these kind of behaviors. So it is a pretty effective tool. Accelerometers can also detect behavioral changes in animals due to disease or pain. Again, if an animal is fatigued or lethargic, it's going to be moving less. So changes in movement frequency and speed can be analyzed by the accelerometers and used to look at disease progression or indicate disease. Recent applications of accelerometers include identifying the onset of a virulent swine disease, African swine fever in wild boar, and looking at how long it took for them to start to slow down and the rate at which they slowed down. It has also been used to detect changes in movement due to systemic inflammation in cattle. Researchers in both studies found that these accelerometers were effective in detecting the changes. In the cattle particularly, the accelerometers detected disease several days before visual observations from personnel would. Unfortunately, the battery life of these kind of devices presents quite a challenge in the application of accelerometers, particularly when they're being attached to wildlife, because it's a lot harder to control where wildlife are, and it takes a lot more energy to track them down to either charge the accelerometer or change batteries. Because of this, in the study of the wild boar, they only recorded 4 seconds every 4 minutes to conserve the battery life. Biometric devices that are capable of measuring basic vital signs, such as heart rate, like those that could be found in your fitness watch, are useful because they provide researchers with a slew of data remotely. This is particularly beneficial because it means that research subjects don't have to come into the hospital or a lab for recordings, and therefore you're probably going to have better uptake on these kind of studies and lose less subjects to follow up. Researchers in China have showed how abnormalities in heart rate and sleep quality often preceded the development of COVID-19 symptoms and used analysis of data from fitness watches at a population level to predict future COVID incidents. In chronic disease, many studies have looked into the association of moderate and high levels of exercise with lower all-round mortality. And again, this was using exercise and heart rate data stored on the subjects' watches. This has also been implemented in the livestock industry with collar devices capable of recording skin temperature, heart rate, blood oxygenation. And these collars, interestingly enough, were actually combined with environmental sensors, accelerometers, and biosensors, the latter of which was used for the on-site detection of a number of industry relevant diseases at a very good sensitivity. So onto computational power, and this is where the majority of my work comes into play. So developments in computing have arguably had the most impact in my area of research. Looking back over the last 30 years, we can see that an increase in the use of epidemiological models as advancements in computing have developed. Back in the late 20th century, modeling was still limited to those who had powerful enough machines to run them. However, during the COVID-19 pandemic, models were at the forefront of the response. In particular, our lab heavily relies on the use of high-performance computing to run our computational models. In brief, high-performance computing involves the use of a network of multiple processors to undertake tasks on large scales and in a timely manner. Some high-performance computers can be comprised of thousands and thousands of processors. For my research, I take advantage of high-performance computing by running my simulations in parallel on different processors, allowing them to be completed simultaneously, and for my model to finish in a fraction of the time. To put it into perspective, with just one processor, it would take 50 days for me to run my model. But with 100 processors, it only takes me 12 hours. And in my research, I don't just run one iteration of my model, I run 10, 15, looking at different scenarios. So this has really benefited by making my PhD research quicker. With the advancements of computing, we've also seen the development of new scientific analyses and the rise of social media, which has provided more and more data for epidemiological research. Examples of this include the use of genome-wide association studies, which allow for the investigation of genes involved with disease, or the use of social media trends that can be used to predict increase in misinformation and the levels of vaccine uptake during epidemics. This was particularly used during COVID to look at the uptake of the COVID-19 vaccine in the public. However, such data is often large and high dimensional, and so this can be difficult for traditional databases to manage. And if you're wanting to store it on site, the data on site, obtaining large enough hardware to store it can be pretty expensive. So cloud computing, where the data is stored offsite by another company. So think Amazon with their AWS. And is accessed and uploaded through the internet, provides a much more affordable and feasible option for researchers, and has really been involved in breaking down that kind of monetary barrier for this kind of research. On to improved imaging. So when researching diseases that are heavily influenced by climatic and environmental factors, having data about the surrounding climate and landscape can be very beneficial. For example, infections of West Nile virus and dengue are often limited geographically by their mosquito vector, which can only survive in certain conditions. So it needs very humid and hot or warm areas. And similarly, the parasite that causes schistosomiasis is limited by its intermediate host, the ram's horn snails, which are only found in warm freshwater bodies, bodies of freshwater. So changes in environmental climatic factors can impact disease incidence or disease distribution because of this. And so by tracking these changes, you can actually estimate or predict the incidence or distribution. The most common way of doing such data is by collecting it through remote sensing. And this is often used through multispectral imaging or LiDAR. Multispectral imaging is the technique used to produce most of the satellite images we are used to seeing. It involves collecting the reflection of light from the Earth's surface at different wavelengths, so in different colors. And these can be stacked on top of each other or compiled together to present true composite images that you might see on Google Earth, or to look at specific features, so looking at bodies of water. LiDAR, which is capable of producing images such as the one that you can see on the screen, is predominantly used for elevation and vegetation height. So in this picture, the cooler blue colors are indicating high elevation, and the warmer red-orange colors are indicating lower elevation. So LiDAR is usually attached to an aircraft, and as the aircraft flies along, they shoot laser beams down to the surface of the Earth. And the LiDAR technology measures how long it takes for this laser beam to travel down to the surface and reflect back and return. So if it hits, it might reflect back when it hits the ground, or it might reflect back when it hits different types of vegetation or tree branches. And so the longer it takes to return back to the aircraft, the lower the elevation. And this is really quite useful. And both of these different types of remote sensing are used in our lab for analysis of swine disease. Additional uses of imaging in epidemiology include the application of thermal imaging. Thermal imaging measures the infrared radiation or heat emitted by all objects with a temperature above absolute zero. In both human and animal health, thermal imaging has been employed to sense abnormal skin temperatures, such as fever, or even low skin temperatures in some animals caused by disease. In the swine industry, it's been applied to remotely monitor the skin temperature of pigs. However, its largest application has been in humans. It has been used in airports around the world during several epidemics and pandemics. That includes the 2003 SARS, 2009 swine flu, the 2014 Ebola outbreaks, and then COVID-19. And it's used to screen for febrile illness or fever en masse. And this is because it is a non-invasive and contactless procedure, and can be done at a distance. However, results from this kind of use in events has shown very varied results. There's been reports of both high and low sensitivity. So it'd be interesting as well to see how electrical engineering could be applied to improve the sensitivity of infrared cameras. So on to future directions and challenges. Firstly, for the challenges, and I think I have covered some of these challenges, but we can go into them in a little bit more detail. As mentioned, the sensitivity of many of these technologies and methodologies, so the infrared cameras and I can't remember which one I had at the start, but that was the particulate sensors. The particulate sensors and the infrared cameras, the sensitivity of these, they are sensitive to external factors, which can make their use challenging. And this is definitely a hindrance to the more widespread application of these kind of technologies. The battery life of a lot of wearable and portable technologies is a limitation for the use of these technologies. As we've seen, they could only record data for small amounts of time when looking at using accelerometers on wild boar. And I know for myself that I have to charge my Fitbit quite a lot, and I often forget. So I wonder how that is impacting studies that are using this kind of technology. I also think it will be interesting to see in the future if privacy laws present a challenge to this kind of research. As our lives become more connected and data-centric, are privacy laws going to change? And if they do, will they change for the better or for the worst? And also, how are public perceptions going to change? Are people going to be more likely to be okay with their data being shared or less likely? And while this isn't necessarily something that I think can be solved by electrical engineering, I imagine it is a challenge that's shared by both epidemiology and areas of electrical engineering. As for future directions, I'm really interested to see the impact that quantum computing can have. In case you aren't particularly familiar with quantum computing, this is computer hardware and algorithms that take advantage of quantum mechanics to solve complex problems that classical computers and even high-performance computers can't solve. And it, again, is even faster than high-performance computing. So I wonder how this particularly will impact modeling research. We saw a huge increase in epidemiological modeling with the advancements of computing that have been had so far. So I would love to see how widespread, even more widespread modeling becomes with the use of quantum computing. And I wonder, is it going to provide us with faster parameterization of our models, allow for larger and more intricate models, and allow for much larger amounts of parameters to be used. I know renewable energy is a big thing right now, especially with a focus on climate change. And I'd be really interested to see how this kind of technology can be incorporated into the electronics that epidemiologists use. Could it be used to solve the battery life issues for wearable and portable technologies? And is it possible to make our research more sustainable? I know that there is often a lot of single-use material in science, and that is no different in epidemiology. So it would be really interesting. Um, and finally, I want to touch on precision medicine. So this is the use of kind of personalized treatments based on your particular health data. Um, and with that, that means we're going to have the access to more and more details about individuals' healths. Um, sorry, I was just checking the chat. Um, and I wonder how this data will be incorporated into studies. And I'm very interested to see how this, like the kinds of studies that will be able to be undertaken once we have more data about human health than we already currently have. And at a much, I guess, easier way to access it, much more accessible. So with that, I'll finish. Oh, and I'd just like to say thank you for allowing me to come on and talk to you about epidemiology. I found it fascinating looking into this for this presentation. And I'd be really interested to see how or what kind of ideas you guys come up with for the use of electrical engineering in epidemiology. And with that, I shall hand over to any questions.
Any questions from participant? Is this similar to federated machine learning?
Could you provide a little bit more detail? Because federated machine learning is not a, I know machine learning, but I do not understand what you mean by federated.
Ma'am, battery life is one of the challenge. So as you said, for limiting factor for the use of wearable and portable technology. So how we can overcome this challenge?
I think I'm not particularly aware of like in-depth information about the possibilities in electrical engineering, but I know that there is constant use into the making smaller and more powerful batteries. And I would be really interested to see the kind of how electrical engineering could be used to prolong battery life. I think either making battery life more prolonged or allowing for kind of solar charging on these kind of devices would be probably the most beneficial. I think solar charging would be the best because then you have a limited, it's practically unlimited. However, for some situations, like for the wild boar, they like to live in very forested areas. So I don't know how applicable that would be because of the lack of sunlight that may get through um, the kind of tree canopy. So, um,
Is any questions from participant?
oh, so sorry, I just did look up federated machine learning. Yes, federated machine learning would be using high performance computing by looking into using different or it would be a way of that. Often the high performance computing that we use is based in one server, but it is possible to connect multiple servers in high performance computing and supercomputers. So yes, federated machine learning would use would be similar to the use of high performance computing. Is there any more questions?
Thank you so much, ma'am, for throwing light on such an interesting topic. I'm sure you have definitely encouraged the participants to pursue this area and work on it.
Okay. Thank you so much for letting
Yeah.
me talk.
Also, we are extremely grateful you have delivered this session according to our schedule. I request you.
Thank you very much.
Yeah, I, I request you to accept the token of gratitude on behalf of organizing team and Yashwantrao Chauhan College of Engineering, Nagpur, for sparing your valuable time and guiding us.
Thank you very much.